This video is to help students understand the diffraction questions we're going to be doing. This is going to be a double slit diffraction. So we do need to know the distance between the two slits here. And that's going to be the letter D. Okay, we do need the distance from the center of our slits, okay, to our screen. Let's call that L. Okay, and we need to identify the pattern that may exist here. Let's say our first bright is located here. There will be an equal bright on the other side. Okay, now the central bright, we don't have much information about that. Okay, but we need to measure the distance from this center line up to there. Let's call that Y. Okay, now again, the center bright, we're not going to have any information on, so we know that's located at 0. So then we do use the equation d sine theta is equal to m lambda. And m in this case is going to equal 1. And we don't know what our wavelength is going to be this time. So that's what we want to try to find. So how do we get the angle theta? Well, the angle theta, if you can imagine, I'll try to draw a hypotenuse here. I'll just draw a dashed line here. Okay, I'm trying to make it as straight as possible. Our theta is located right here. Okay, so we have this L length here, and we have this Y here. If you can imagine, this is a triangle here. So then I can just say the tangent of theta is equal to Y over L. And take the inverse tangent, and that'll get us our theta here. Now again, M is our first maximum, so our first bright. And if D is known, then it's really easy to find our wavelength. Now you'll be doing a simulation that looks very similar to this, and you'll need to make the measurements of L and the measurements of Y in order to actually calculate the wavelength of the light that's shining. Diffraction gradient lenses are done the same way. If this light is incident upon this lens here, now the slits in this are very, very tiny. This one says 5,290 slits per centimeter. So what we got to do is, in order to find D, then I need to take 0.01 meters and divide that by 5,290. And that number is easy to figure out when you figure out this. So D is going to equal 1.89 times 10 to the minus 6 meters. So that's something you need to know in order to accomplish a diffraction gradient lens too. Now you're going to find the wavelength of blue light, green light, and red light. Very similar. You need to look at the distance from the screen here. The screen to the lens is 20 centimeters. So then we're going to need to know the distance from here out to each one. So for blue light, this would be my Y, and the 20 centimeters is my length L. And then I can use tangent theta, again, equals Y divided by that L to get my theta. And then I can use D sine theta is equal to m lambda, okay, for each one. And m, again, is going to equal 1, okay, for each color of light. Because this is the first blue light that we see, this is the first green light that we see, and that's the first red light that we see. So diffraction gradient lenses can be used to actually split the colors of the rainbow up, and then you can figure the wavelengths for each of the light that come out. And of course, the colors repeat themselves as they go farther and farther out, but we don't need to see that. We just need to see the first one for each of the colors. So again, measure the length L, which we know is 20 centimeters in the simulation. And then your job is to measure the length to the actual colors that you see in the simulation. Okay, and that's all you got to do. Should not be too bad, but ask me questions if you need.